Thanks everyone for coming, and thanks to the organizers for inviting me to give this talk. It's been a pleasure to sample a bit of the more condensed matter and different physics talks over the week. I'll try to appeal to that sensibility as I talk through some of our recent results, and yeah, hopefully you're as excited as I am about new opportunities in understanding how quantum computers help us kind of contextualize different sorts of sampling or generative advantages, since we all probably use these days generative models. So, yeah, what is a generative model? I think it doesn't need much explanation these days, considering most people have used something like ChatGPT or Gemini, maybe for their research, maybe just for fun. But very generally speaking, it's just a model that can be used to generate new data instances from some probability distribution. So, transformer networks have gotten a lot of attention, and the basic kind of model that they often use when they're trying to do text generation is some kind of conditional generation, where you have something like a prior text, the students open there, and then it tries to sample some next word based on the text that it's seen, like the students open their minds. And in this talk, I want to kind of relate these to things we know about in both physics and quantum computing, where they can be more general objects than just tokens or words. Maybe they can be quantum states or quantum circuits. So why might you think that this is a good avenue to go down? Why does this make any sense? And this is something we've been thinking a little bit about, especially since early demonstrations of random circuit sampling. So if you recall, this was an early experiment by the Google team that then it's been followed on by many others, and updates to this experiment, where basically we wrote down a random circuit that was mapped down to superconducting qubit devices. Of course, if you're not as familiar with these, you just kind of read them like music notation from left to right. Each one of these is an interaction we do on each of these qubits, and at the end we measure something out. And in principle, what this let us do was describe very compactly some probability distribution we could draw samples from that we didn't believe, at least in a large size limit, is easy for a classical computer to do. So it gives us efficient access to some new probability distributions, which sounds very exciting. And that sounds like something you should be able to use in AI. And so what did this lead us to do? We already had some interesting techniques and models that we had used on, say, physics type things, so kind of like variational methods, variational quantum eigensolvers, where we just kind of move down here and map each of these qubits onto the same kind of notation, but now give each of these gates some kind of adjustable parameter. This lets us do simple measurements and kind of do an update loop. And if you kind of squint and look at it, it looks kind of like a neural network. There's, of course, some big differences between them. This is kind of more like parametrizing a Markov chain than it is like perhaps a function. But you look at it and you're like, okay, I could kind of see the similarity. A lot of machine learning was done empirically. Why not give this kind of model a try? And so this feels very enticing. We know about the existence of models that are sort of, we can sample, that are beyond classical. And we feel like we have some idea of how to train them. But the story hasn't worked out quite so well to date, in part because this second step has turned out to be a lot harder than we would have liked it to, for various reasons. So as a matter of kind of history, the reason we started looking at this barren plateaus problem, which is a problem with concentration of measure, you randomize circuits, everything comes out very flat, it's very hard to train, was that we were hoping to use something like this on the kind of beyond classical circuits, and these were the ones that were exactly in this regime where everything concentrated. So the same features that made it hard to sample from classically appeared to make it impossible to train. And so it's hard to call it a generative model if you can't actually put any data into it. You can just kind of like take it at random and you get what you get. And then you can try to make these models shallower, which we can kind of alleviate this problem. And I'll say there's been many other solutions to this problem as well that have their own benefits and drawbacks. But even when you make them very shallow, you kind of move out of any chance of having this over-parametrized regime, and then you're just swamped with traps that are everywhere, and this kind of a visualization of these landscapes. So you're left with either deep circuits that are concentrated or shallow circuits full of traps. You're kind of like, okay, well, what can you do with this? How can I get a model that could potentially be beyond classical while also being trainable? And very recently, we've made progress on this problem, starting first with how to efficiently learn shallow quantum circuits, and some of the co-authors of this paper, of course, are here, Robert and Yun Chao. And we wanted to ask, after we'd done this work, could we leverage this into making it look more like a classical or quantum generative problem that people would care about, as opposed to just the kind of restricted setting of the shallow circuit using the same technology? And so to give you just a very informal definition, what do we want? We just want to be able to learn to generate some desired outputs better, faster, or with less resources than we could with just a classical computer. And for us, this is going to look like a task that's kind of the intersection of a few simple Venn diagrams to set it up. We want something that's quantumly easy to generate. So for example, the supremacy circuits had that, but they were not easy to train. We want it to be classically hard to generate. And we would like it to be easy to learn, given some simple classical samples. So I give you a few samples from this. I can learn it, and then the thing that I learn is hard to generate without a quantum computer. So, was there a question? Sorry. Okay. No. All right. And so one candidate that we came back to, because of this efficient learning technique, and because it's experimentally feasible, were shallow circuits. And so there's a lot of interesting studies that have been done on shallow circuits that it can be kind of counterintuitive. So for example, when your circuit is shallow, going from left to right, the light cone causal light cone of this output qubit will be only a very small subset of the input qubits. And what this means is that local observables are often very easy to calculate, but somewhat counterintuitively, for most distributions, full samples are still classically hard to stitch together. And this is the kind of tension that we're going to use to make something that's trainable but hard to sample from. They're experimentally friendly. They don't have this problem of barren plateaus. And until recently, they were often conjectured to be hard to learn. And the reason was that, at least classically, there were ways of efficiently learning shallow classical circuits where you could really leverage the causal light cone. But the problem was, in quantum mechanics, the non-locality of states you could generate, even in constant depth, made it very tricky to disentangle what was responsible for what, and you were often left with combinatorial approaches. But now we have a simple divide and conquer learning scheme with completely efficient classical learning that I'll describe later, but I'll describe kind of a specialization of it first. And the theorem from that paper was, surprisingly, any n-qubit shallow quantum circuit can be learned to diamond distance epsilon in polynomial time. And if you're not familiar with diamond distance, it's kind of a very stringent error metric. It means worst possible observable on worst possible input state you could give will have error at most epsilon with high probability. And so what we did for this was kind of take that base foundation and leverage it a bit to go something that looked more like a generative problem. So there's a few things to take care of, including which distributions can be learned, which ones are locally tomographically complete, things like this. But basically, we proved that there are distributions mapping classical bit strings to classical bit strings that a quantum computer can efficiently learn with a small number of classical data samples and are hard to generate with a classical computer. And so how are we going to do this demonstration? So we not only wanted to have some proofs kind of underlying it, we wanted to get a feeling for where this might happen on a real experimental device. We won't quite go into the beyond classical regime, but we'll be able to use previous results to get to it. And to do this, we needed to at least solve one small issue with shallow circuits first, which is that when shallow circuits are hard, there is some sort of kind of conservation of space-time hardness, and you might not expect that a shallow circuit would be hard on very few qubits, and you'd be right. And so for shallow circuits, we often need huge numbers of qubits to make them actually hard, but we wanted to find a model where we could be a little bit more experimentally friendly on the devices we have today, and we're going to leverage a shallow to deep mapping. But to kind of give you a 2D example first, we'll actually use 3D shallow circuits because of our 2D grid later. But given kind of n by n inputs, so you're just looking down on some number of qubits, time is going to flow out of the plane, but we don't do very many operations. This is just Hadamard on all of the qubits, depending on each of the n by n input bits, classically controlled. We do an RZ with our one adjustable parameter per qubit. We do a CZ between the connected ones that you see, and then measure everything in the X basis and assign that to Y. So that's the entire learning model, basically. It's shallow, and the shallow structure, because of that kind of causal cone structure, makes it easy to learn, even though in the large size limit, this will be hard to sample from. And so this is a constant depth generative model parameterized by these parameters beta. And like I mentioned, some of these shallow circuits are maybe only hard in like a real factor sense as you grow them to say 1,000, 10,000, 20,000 qubits. But that's not what devices today typically look like. At least in the superconducting world, we'll often have, say, 50 or 100 or 200 qubits that we can do deeper circuits on with high fidelity, but we don't have, say, thousands, tens of thousands, or millions of qubits yet to be able to do these shallow things. So we developed these models we're calling instantaneously deep quantum neural networks due to some vague connections with IQP circuits, though they're not exactly IQP, but we show probabilistically sample very deep circuits. And so we do a mapping. This is just an example of 2D into 1D, where now time goes from the bottom to the top instead of out of the plane. And at each one of these steps, we do some kind of measurement and feed forward in the general case to kind of map between the two, but we'll actually specialize to a case for these experiments that's the hardest quantum circuits, but we don't need feed forward. In general, we would need it to do the full distribution. And so what do we do for these experiments where we want to show some kind of beyond classical learning trajectory? How do we want to emulate each of the components to understand what they are? The rough experiment outline is we generate a 3D shallow circuit because we're going to be on a 2D superconducting grid. We give each of those qubits a parameter beta, and then the kind of number of shallow qubits is going to be determined by the number of physical qubits times the model depth. And so we have around 68 physical qubits we use for this experiment, giving us an effective shallow qubit count of around 800. Because this model is local and that learning technique I mentioned but haven't described in detail yet is efficient, we can simulate the learning of this. And this is one of the big conceptual disconnects for people. You can kind of learn these models locally, but the inductive bias on the global state, once everything is stitched together, is still hard to learn. And every step of this is kind of provably efficient and checkable, where if you get every individual error below a certain level, you can precisely bound the error that the eventual samples will be from. And so we then train competing classical models on the same bit string inputs to try to compare their performance. And then we do inference on the quantum device to take samples and check it for regimes that we can check it. And then we'll do one final trick where we'll go beyond the experiments we did and show a mapping technique in order to evaluate performance on a much more full throttle experiment, I'll call it. So what do, roughly speaking, the results look like? And I'll go to, this won't include, for example, the beyond classical regime yet. So what is this picture? This is the n shallow qubits. Again, that's the physical qubits we have, times some model depth, where we increase the model depth in order to increase the difficulty, and that's really just increasing depth on a superconducting qubit device. And we compare the sort of fidelity of the total output distribution as far as we can on these. And we compare basically learned values that are simulated on a classical computer, so perfectly, to show that the learning is sort of working. We also compare traditional classical models that are good at sequence-to-sequence learning, but again have no knowledge of this quantum inductive bias. So you might say that's a bit stilted, but we'll get to a more realistic comparison in a second. But you can see that these kind of classical sequence-to-sequence learners on the same input do very poorly in the sense that their fidelity tanks quite quickly as a function of the number of shallow qubits. And then this is real kind of experimental data where we compare the quantum experiment on the learned data, the ideal showing the learning is working, and also we use a Clifford proxy that we show tracks performance quite closely so that we can very quickly evaluate performance to large sizes, though that would not be any kind of beyond classical. So you might say, okay, well, you compared to something like transformers and XGBoost with big models and lots of training time, but your quantum models were clearly better, or just because they knew where the structure of the data generation they can sample from quantum. So a better comparison would be to as fast of simulations of those quantum models as you can, so it would be kind of like a quantum-inspired model that you're looking at. And so how do we do that? Well, we wanted to reuse the efforts of the team that had done a bunch of beyond classical experiments to try to infer model performance in that regime, and we actually leverage this kind of distributional nature of the circuit, so they sort of have a distributional universality, so we can map to one representative from an exact beyond classical circuit that was run in another experiment and precisely evaluate its performance. In order to do that, we start with some experiment that's already done, a very hard, dense random circuit sampling experiment. We can decompose this into the model form I talked about, and that will give you a family of circuits now that you can learn from efficiently, so it won't be the same access model as the original RCS, which will be a bit different. We can simulate learning with data because it's efficient, map back to the original circuits, and evaluate gate learning errors. And this tells us kind of number of samples you'd need to take from the device in order to get each of the model and gate parameters below a certain error. And you can see even with kind of 1 million samples, which is, a few seconds on many of modern superconducting devices, this is enough to learn all of the parameters in the circuit to a degree of accuracy better than you expect your typical gate infidelity. And then this lets us take a slightly larger step. So this is the same graph you saw before, but now we can leverage previous work from Morvan et al., which is an updated quantum supremacy experiment, to kind of extrapolate where in terms of top superconducting or top supercomputing implementations of tensor network contractions, you would get a crossover into the beyond classical regime, and you can guesstimate or kind of bound now based on this where the crossover would be for a beyond classical efficient learning model. And we kind of guesstimated around, if you're willing to spend, many frontier years on this, around 34,000 shallow qubits, which means this gives you kind of a ballpark of where this crossover is. And again, this is based on experiments that were done just without this component of feed forward. So since I have enough time, I'm going to pivot slightly and tell you about the quantum side of the story. So that was kind of an interesting story for us because it was about mapping classical inputs to classical outputs and it being entirely efficient to sample in this regime, though again, this is not structured in any way that we know, for example, an empirical problem distribution would be interesting. I figured for this crowd, you might be interested more even in the second demonstration that we do, which is how do you work on, say, directly on quantum generative models. And this means learning quantum circuits to some extent. So here's an interesting theorem that's relevant for, say, if you want to obfuscate circuits or you have a Hamiltonian evolution and you don't know how sort of concisely it can be expressed. So given a general polynomial-sized input circuit, and I promise you it definitely has a constant depth representation, finding that constant depth representation is not efficient unless, or classically, unless quantum computers are about as good as classical computers. And yet this algorithm that I'll describe shortly can give you this solution efficiently. And so you might think this is a very nice tool for compressing physical dynamics, understanding the extent of complexity of dynamics, or just telling you interesting new circuit compilations. And the very brief algorithmic sketch that I'll give you is that essentially the trick works by a divide and conquer sort of scheme, where it turns out that what I want to learn is sort of unitaries UI that are local inversions for each qubit. And so this can be a bit tricky, you would think, because I want some local unitary based on some local measurements that turns the action of the original unitary into the identity on a particular qubit. But if you find these for different qubits with overlapping light cones, they might not commute. And so you'll think that this is kind of what's going to block you from doing this procedure. But it turns out there's a very simple trick where as long as you learn each of these local inversions, you can apply them in any order and you don't need them to commute, and it all sort of works out. And this is kind of the nice trick that turns causal learning into one that works completely in the quantum space, and you don't have to worry about all of the non-locality problems. And so the sketch, once you have the trick that I'll show you in one slide, is you do random local state preparations and measurements. So you just give it random, X, Y, Z basis states, do random local X, Y, Z measurements. Offline on a classical computer, it's efficient to learn the local inversion. And I have to, be careful here. Efficient meaning because the light cone never grows, I can in principle do brute force enumeration and that will still be efficient, but I'll actually show you that for real problems it often works out better than that. And then I will apply the forward direction with what's called the sewing trick, which is the trick that lets the causal light cones be good for everything. So what is the trick? I'll just show you a graphical circuit proof in a few lines. So imagine that I have an ancilla register in any state, and I've found each of these local inversions by offline optimization. Now, if each one of these, so this is the local inversion U1, this is the local inversion U2, so turns off qubit 1, turns off qubit 2. Now I just tell you I'm going to apply U1 inverse, swap with the ancilla register U1, and repeat this for each of the qubits. Now I want to see what this action does. So this is the only thing I'm actually going to do on my quantum computer. So I'll insert first the identity, U dagger U up front. This is the thing I'm trying to learn and trying to apply. I use the local inversion property to note that this is now the identity. This lets me swap this qubit forward, combine these two, they drop out, and then I'm left with this object. I repeat, and then I finally just swap the qubits, and now I learned that by doing this thing, which was counterintuitive, and I could have done it literally in any order, I get exactly the unitary I want on the original register, and I'm free to throw away the other register if I want, or do more operations. This is kind of the core trick to all of this. It's not very intuitive why it works. You can work out the intermediate steps of quantum states and look at what's happening, and it makes no more sense than before. So I think this trick has actually been noted not in the context of learning, but in the context of quantum cellular automata some time ago about causal cones, but that also added no insight to myself. So yeah, if you find some good intuition, do let me know. And so we can use this more general version to try out an application. I'm not going to claim this is any kind of beyond classical, it's just kind of cool, which is we can compress physical dynamics when they are compressible, or you could approximately do it when you don't know them to be this way. So for example, we could sample very short and very long times of some Hamiltonian dynamics applied to an initial state. And we can build it from a Hamiltonian we know secretly to be compressible. I'm not claiming this is kind of cryptographically secure. You might be able to stare at the Hamiltonian we use and tell yourself. But we're going to learn it each time, evaluate the error in learning, and for the first time do a full demonstration on the device of the entire swap networks that I just kind of alluded to. And the unitary we're going to use to hide this is some sort of randomly drawn sequence of 1 and 2 qubit gates where you expect these Z's to kind of be pushed out into all kinds of linear combinations of up to, say, 4 local operators. Yep. No, they're totally like this is kind of the unitary here. Each of these operators are the A's and X's are chosen like as real numbers. It's continuous numbers. Yeah, that's right. That's right. And then this is kind of the experimental setup. We did this on a smaller number of qubits because we had to fit this onto the kind of snake formation. So each one of these system and ancilla qubits, they're a bit harder to pack into space while you still want to do a lot of operations. We basically learn the local inversions. We run the sewing for the first time really on the chip. We sample and record the observables, and we choose some kind of learning ansatz to show whether this can be efficiently learned, and not just through brute force enumeration, but through kind of like, does the landscape look okay? And we decompose it into pieces. This is kind of an experimental detail that if you chunk things up, you can learn not just on 1 qubit at a time, but you can learn on 4 qubits at a time. And it's really any constant number, and this sometimes helps a lot with parallelization. We train and learn each of the pieces. We swap them in, we run them, and this kind of shows you that even without much error mitigation, despite being a 40 qubit circuit, this works quite well both at the very short times and very long times, which you should expect from kind of the learning theory that this didn't really make a huge difference for our learning. It's just kind of a demonstration that when this Hamiltonian and unitary are truly compressible, this algorithm can find it and it doesn't make any difference. Whereas if you had run this with like naive Trotter, looked at the Hamiltonian, not tried to diagonalize it, you would have had many, many thousands of Trotter steps to get to the same point. And so as a final note, I guess I am doing pretty well on time. I'll be a bit early. You might ask, about that step of learning, like why does this become efficient when we do this divide and conquer scheme? So it turns out that when you only need to learn on 1 of these qubits at once, you don't have nearly as many of these light cone collisions, and these turn out to be what create all of your local minima. So when you're truly able to break this thing up, And we look at kind of a very stilted problem I haven't described here, but it's entirely classical, just trying to learn a swap network of things that are on nearest neighbor qubits, where our ansatz nearest neighbor, the thing we want to learn, is sort of second next nearest neighbor. And you can look at the landscape, kind of as we alluded to earlier, on random projections in 2D along the different parameter landscape, and they basically all look like this, a chaotic sea of local minima with the true minimum somewhere in the middle. And then when you break that off and do only one qubit at a time, the landscapes look comically nice, to the extent where if you just do restarted gradient descent, it succeeds with probability like 99.99% for this problem. So not only was it efficiently learnable in the sense that I could do brute force enumeration and the number of minima doesn't grow that much, the landscapes are also much nicer too. And I've been thinking of ways to try to bring this beyond unitary learning, but yeah, it's still at work in progress. And so, yeah, with that, I'll kind of summarize what we went through. It was kind of a lot of information at a high level, but I hope it interested you to learn more or ask some questions. So what we tried to do here was close the loop on generative quantum advantage. And what I mean by that is we had distributions that were hard to sample from before, or we believed were, and we wanted ones that were hard to sample from and easy to learn, and a technique for learning them and kind of implementing them. And that's what we've tried to do here as an experimental demonstration. And so we kind of supported this, not claiming we're in a beyond classical regime, by showing comparisons to modern sequence learners up to around 800 effective shallow qubits, meaning 68 physical qubits, depth 12. And we used our exact mapping, which I didn't describe in too much detail, to infer efficient learning and kind of bound or estimate where the beyond classical model threshold would be at around 34,000 shallow qubits. And we showed a physical evolution circuit for the first time implementing experimentally this sewing trick up to 40 physical qubits, and demonstrated an improved learning landscape that made all of this possible. And with that, I'd like to acknowledge, of course, the key collaborators for this particular project. Of course, Robert and Michael were crucial, and all the others helped with experimental design, calibration, and support. And with that, I'd like to thank all of you as well.
Questions? Oh, you're not.
So it's really nice that you have a scheme to, I don't know, not get trapped in the barren plateau. But, you know, when you started with the generative model, and the generative models that we experienced and the way the whole machine learning field developed is that there are problems that people want to solve, or, you know, tasks that people want to generate. And I think one of the biggest challenges is that those problems that matter to our everyday lives are classical. Mm-hmm. So here you have a problem which is intrinsically quantum, and in learning that distribution, which is designed to be very hard classically, your quantum model did better than the models that were designed to predict languages, right? Mm-hmm. And that's nice, but at the same time, not surprising in a way. So what is the prospect of being able to take what you've learned here and being able to do something that, you know, is a problem that people would have liked you to solve, mm-hmm. not the problem that we invented, that we like it, but it's in this room, right?
No, it's a great question, and I think it's one we all have to contend with. It's certainly, if we knew such a problem, we would do that one instead, I guess. And so I would say that, you know, the prospects for where we can find separations on problems we really care about, I'm going to kind of guess that that's going to lean a little bit on empirics in the future that we're not quite able to access yet. And maybe this is not going to be a satisfying answer, but we're restricted a bit now in our ability to kind of edge out and show where we think quantum computers might have an advantage by what we can kind of reason is hard or maximally separates the two by pencil and paper and then kind of small demonstrations. And if you look classically at kind of the history and the development of machine learning, in the 70s when things were kind of limited, people developed theories of kind of like pack learning and other techniques to try to guess what computers would be good at learning. And what we could show with pencil and paper was that they could learn almost nothing. And rather than give up, people pressed forward. And eventually, empirically, it became very, perhaps surprisingly good at certain problems. And so I agree, these are a little bit unsatisfying because we have to put our thumbs on the scales to find anything where we have a separation, especially at very small sizes. Like, it's very hard to compete with 10 trillion parameter models when you have like 40 qubits. But I agree with you, this is a direction we need to go in, and I think one of the things I'm excited about is trying to figure out how we get these models to scale better, because the principle that has worked classically has often been to kind of abandon theoretical support and focus on getting the most amount of compute and resources into the practical problem that you can. And as we've scaled, we've just been surprised over and over again with how well they've done. And I worry that we won't be able to see big separations on practical things till we have bigger devices, but at the moment we have to keep putting our finger on the scale. I'd like to get away from it as quickly as possible.
But are you sure if the scale is what's limiting? Like, in the machine learning history, right? Mm-hmm. Figuring out what was a bottleneck, like what's mm-hmm. making it really hard, was also really important, right? So do you think it's the scale that's the bottleneck here?
I mean, for this, the scale is definitely the bottleneck, just because I could, in a certain sense, I could run a classical network on this if I had enough scale, and I could do as well as classical, and then I only have more degrees of freedom to apply at that point. But it's a little bit of an unsatisfying answer, because we'd like to do a lot better at a lot smaller, I think. It would be nice if you didn't need, 1 trillion qubits to match like a terabyte of classical bits. That seemed a little bit wasteful, but yeah, I don't know if I have a better answer other than I agree this is an important problem.
Thanks for a nice talk. You might have already explained this, but I missed it. So when you benchmark your generated advantage, sort of you're relying on the fact that classical simulations of that shallow circuit is difficult, but then there were quite a few works, including recent ones, and also like maybe back in a few years ago, where people could discover that if you have noise, actually that would undo the advantage drastically. So there are some clever tensor network methods which you can employ to actually sample the circuit efficiently if there is like a non-zero amount of noise.
Yeah.
I'm wondering whether you guys have thought about this, or is it like more like just extrapolation of, or did you guys try out all these methods, or is it like just, I'm not sure.
So yeah, we actually punted on this one a bit. This is why we leaned so heavily on the fact that we have an exact mapping to existing beyond classical results. So we're able to take a circuit that was worked on here, which was kind of a deep superconducting qubit circuit, and show that our model maps exactly into it. And then we're able to leverage the fact that the individuals that worked on this paper, as you suggested, spent, I would call it, many man-years optimizing tensor network simulations in the presence of noise, hyper-optimizing contractions, running on decades of frontier time, et cetera, and they very much looked into those. And so we're able to kind of lean on the fact that these circuits, to the best of our knowledge today, represent kind of the premier simulation techniques in the presence of noise for these circuits. And so you might say, for example, if you're looking closely, that this mapping applies to the hardest possible quantum circuit. And so as we sample from a more general distribution, there can be circuits in the family that are a bit easier to simulate. So depending on their weight in the probability distribution, that can lower the simulation difficulty. But if we heavily weight on purpose the harder ones, we can kind of circumvent that.
Okay, thank you.
Classically, I suppose people use usually deep neural networks. I'm not an expert, but sort of, do you think sort of shallow circuits will be sort of the go-to? I guess once you have a very large device, are you going to sort of mostly focus on shallow circuits, you think, or do you also want deep circuits eventually?
I think it's a great question. People do, of course, focus these days on deep networks, so sometimes deep can only mean a few layers or something like that. But the thing, I think you're drawing an important point, which is what pushed us to shallow circuits was the element of trainability. And I think that has driven a lot of the evolution of classical machine learning as well. So there's sometimes, in principle, a more expressive model that you know about. For example, recurrent neural networks in some principled way are more expressive than, say, transformers, but transformers kind of unroll a recursive loop and can train with far more hardware. And this is this kind of push towards the thing that has driven it is sometimes ignoring your best instincts and going for scale. And I'd like to see more quantum models compatible with that. We don't have a lot because of these trainability issues. And the shallow circuits are the best we've come up with to date. There's also been some work on commuting, like IQP circuits that have nice trainability properties. I would like something more universal, deeper, and like fully efficiently trainable, even with like backprop scaling, which I didn't talk about today, but we don't have that at all in most quantum circuits. So yeah, in short, no, I don't think shallow models are the future, but I hope we find some insights that let us go deeper, bigger, more efficiently.
Okay, I would have another question.
Sure, yeah.
So even though shallow circuits are not the future, I was wondering if you thought both in the sort of on the learning side, sort of in the circuit learning side, but also for sort of the machine learning stuff about sequential circuits. Like a lot of people are interested in some form of sequential circuits where you sort of you have array law states essentially. So like, you know, MPS is like a sequential circuit, and you can efficiently learn it. You can generalize this to 2 dimensions. And I was wondering if there's any results that, or like, have you thought about using sequential circuits instead of sort of shallow circuits?
Yeah, it's a good question. I might have to ask you later exactly what you mean by sequential circuits. Maybe I'm not familiar with that term, but if you mean kind of like the general
so
tensor.
Like a bit of like a pyramid, so you just
things like Mera
and
tensor
grow
networks
in one
and
direction. Sorry?
things like Mera tensor networks, stuff like that. Is that?
Yeah, not quite Mera, but okay.
Okay. Yeah. I guess maybe as a general response to that, I do think there's some meat left in specialized circuit ansatz families, especially ones that have particular structures that might be beyond shallow, maybe tree-like, that allow efficient training, but we have some belief that it is much easier to run them quantumly than classically, and we still have some notion of trainability. That would be a great step beyond the shallow circuits. Yeah, sure.
Misha?
So it's kind of continuation of this question before, so, and it's about kind of space-time trade-off. So are you kind of, I think you indicated that if you had like a big system where you could maybe do some feed forward, but I mean, of course, finite gate fidelities, that would kind of be qualitatively different from what you can do on smaller systems. Is it the implication? You know?
Yeah.
Is it clear actually, or not so?
So I'll say that we did use a mapping that if you use it for all of the probability distributions we wanted, it would have required feed forward in the sense of having the exact correspondence between that very large shallow circuit and the deep one we want to do for all possible inputs. Whether I'm saying that is accessing circuits that would be inaccessible without it, I'm not sure, but we don't know about the trainability of the more general versions that would have feed forward. I'll say for other reasons I would be excited about training feed forward, of course, and more general classical compute on the measurements in between. I think this adds a lot of power, as we know from results about, say, scrambling can happen even in constant depth if you have classical communication and things like that. So it really makes you more use of your quantum resources. I think the thing I'm still worried about is how do we find models that include it, that are more general, and we know to be efficiently trainable. And I'll say that, like, maybe we don't need provable efficiency. Maybe it would be enough to see empirical great success. But I think that's an exciting direction, yeah. And maybe in combination with Daniel's question about, are there specialized models beyond, like, kind of spiritually constant depth that allow you to get this, like, great trainability?
So a small clarification on these kind of IQP-like circuits. So here you're doing Hadamard, RZ, CZ, and then Hadamard again, presumably?
Let's see.
Before measuring?
Yeah, I think that's roughly speaking right. For the shallow version of it,
yes.
That's right.
Okay.
There is like a little bit of
basis. Yes, is that good?
Yeah, there's a little bit of nuance in just like the input bits are classically controlled in H. But yeah, apart
I
from
see.
that, that's
All right. And then the statement is that this 3+0 IQP-like circuit maps onto this 2+1D hard circuit that had been optimized.
That's right, exactly.
Fantastic. Okay. And then another question is if you could kind of unpack that light cone stitching method a little bit more. It went by a little fast.
Oh, yeah, sure. Let me try to give a little more description of how that works. Let's see. So at least in the kind of learning direction, all we're attempting to do, and then I'll say what the next slide on what the stitching does there, is we kind of, for each qubit, give it a randomized measurement, kind of X, Y, or Z basis, and randomized input X, Y, or Z kind of, plus or minus 1. We collect a bunch of statistics, and we kind of bound the statistics we need. It's like log in the number of qubits versus some precision parameter. Now we take our data set offline. We go and we can kind of simulate the effect of the sort of local light cone as applied to those input measurements. And we're looking, as we iterate through all of these gates, for the ones that makes the effective map that we measure on like the reduced local system into the identity. And so once we've identified that for each one of these qubits, and I can just kind of, there's at least 2 or 3 different ways of doing this. If you care about circuit complexity, you can do raw iteration. If you care about just getting it exactly right on the first time, there's a way to do it as an SVD, but then you have to go recompile your gate sequence, which can be kind of annoying if you have very short circuit budgets. So then you say you know the identity of each of the local inversions. You feel good about that. And now you can use that to implement the overall unitary U. And again, to walk through why that works, kind of the simplest way is just to watch it happen in a circuit diagram. I don't know if you considered this helpful to walk through again, but yeah. Basically, you found each one of these local inversions. So I've applied it to both the ancilla qubits, which could have been an infinite temperature state, could have been 0 state. It will generally be like a small causal light cone, but might overlap and not commute with U2 or something like that. And I just have a set of ancilla registers, and what I'm going to do is apply my local inversions for each of the qubits and then swap with the corresponding system and register qubits. So I have 2 n qubits going along, and at the end of this, I will get the unitary and inverse of that unitary that I'm looking for. And so one way to see that is to say, this is what I do on my device. Now I'm going to do symbolic manipulation to show you that what this does equivalently. And I insert the identity, which is just the thing I wanted to learn and its inverse, so that will always just be the identity. This local inversion property means that when I combine these 2 together, I have an identity channel on this qubit, which lets this swap gate move through these 2. And so once I've moved the swap gate through, this local inversion and its inverse then cancel together and disappear. And I'm left with this circuit here. So then I have U dagger U inverse. And I'm going to repeat that procedure for the second local inversion, where I combine these together, the swap gate moves over, and then I'm left kind of with the, so once I combine these 2, it's identity, this moves through, combine them, and I'm left with this, rearrange the qubits, and now I've done the unitary exactly.
Great, yeah, very helpful, thanks.
Yeah, sure. Yeah.
Okay. Let's make one quick question while done.
So I just want to ask, like, what the background on the project. So why do you want to learn a quantum circuit? I mean, when you want to learn the quantum circuit, that means there is some hidden quantum circuit to begin with. Why is it the case?
Yeah. So it's a good question. One particular scenario could be where you're given a representation of a circuit, and you suspect it could have been expressed as a much smaller circuit, but you don't know its compilation. You can attempt to learn it in constant depth. Another case is if you're more in a quantum learning scenario, you might imagine that the unitary is being applied to some system and no one actually wrote it down for you. Maybe you're trying to do something not quite like Hamiltonian learning, but just trying to learn the process applied to a system, but no one's given you the gate description. So those are 2 scenarios. And yeah,
Let's thank Jarrod one more time.